Okay, so in this video I'm going to go through the task 1 questions. So the first question asks about the drag. It says the drag lift pulls the skier from the bottom of to the top of the ski slope, and the arrows represent the forces acting on the skier. So which arrow represents the force pulling the skier up the slope? So you can clearly see this arrow is pulling the skier up the slope, so that one must be D. The next question says which arrow represents the normal contact force. Now the normal force is always a force that is at a right angle to the object. So you can see we've got a right angle here. So what object is at a right angle? Sorry, which arrow? Sorry, that is C. So it's this one here, which is C. Okay, this would represent the resistance, and this would represent the weight. Now the reason that's at an angle is because it always acts down towards the center of the earth. So B would be gravity or the weight of the object. Okay, the next one, the drag lift pulls the skier with a constant resultant force of 300 newtons for a distance of 45 meters. So we know that the force is 300 and we know that the distance is 45, so we just multiply those two things together. If we do that, we get 13,500, and the answer is in joules. Remember, because it's work done is energy transferred. This is the energy transferred in moving an object or moving a person. Okay, so with the slope, it says at the top of the slope, the drag lift and skis back to the bottom of the slope. Show how the velocity of the skier changes with the time as the skier moves down the slope. After 50 seconds, so I'm going to highlight that, the skier decelerates at a constant rate, coming to a stop in 15 seconds. So after 50 seconds, we've gone another 15 seconds. So that means we're going to go to 65. We'll put a little line at 65, and that's where we're going to go to. Now with a ruler you would need, because this is decelerating at a constant rate, we're going to get a straight line. So from there, make sure you use a ruler from that point, and then that would go to 65. That has to be a straight line. Now that's hard to draw with this computer, but make sure you've drawn that as a straight line. So from that point straight to there. Okay, the next question, it says when the forces are increased on the plasticine, okay, so what's going to happen to the plasticine? Well, if we alter this plasticine, if we pull it that way and that way, when the force in it, it's either going to snap the plasticine or it's going to stretch it. So we're going to see that it stretches. When the forces are removed, it's going to stay as it is. Okay, this is not a spring, so when you stretch plasticine, it remains stretched. Okay, the next question is about pushing, so the force is going inwards. We're not stretching this spring, we're pushing it in. So when the forces are increased, we call this compression. We are compressing the spring. Okay, when the forces are removed, it's going to have energy and it's going to push the spring back to its original shape. So we're going to say that the spring returns to the original shape. Okay, what about this ruler? Well, most of you know this because people twang and bend these in class. So when we put force on a ruler, what's going to happen to the ruler? The ruler is going to bend. Okay, and if you put too much force on it, it may even snap, as some of you have probably found out. And when the forces are removed, well, if it did bend, it's just going to return to original shape. So return to original shape. Okay, if you snapped it, it wouldn't return to its original shape. So you're better off putting bend, and then you can say that it would return to the original shape. Okay, the length of the spring with no load was 15 centimeters. So here we're just talking about the increase in length. So we've got a spring, and its total length before putting anything on it is 15 centimeters. The load needed to produce an increase in length of 2 centimeters. So we're asking how much weight do you need to put on to make it extend by 2 centimeters. So what we're going to do is we're going to go to this increase at 2 centimeters, draw a line across, and we keep going until it meets the line. If we go down from that point, you can clearly see that's 1.5 newtons. So we need 1.5 newtons to increase the length by 2. The increase in length produced by a load of 2.3 newtons. So we're doing the opposite this time. Now we need to look at the scale. Halfway between is 2.25. So an extra block is going to give us 2.3. So that's going to be there. Okay. Now if we look there on the graph, you can go across and that's going to give you this number here, which is 4. So we're going to say that that is 4 centimeters. So a load of 2.3 newtons will increase the length or extend the spring by 4 centimeters. The length of the spring when the load was 2.3. Well, we know that the original length was 15 centimeters and it's extended 4 centimeters. So 15 plus 4 is going to give you 19 centimeters. Okay, the next question. When a force is applied to a spring, the spring extends by 0.12 meters. Calculate the force. So force is equal to the spring constant times the extension. We know that the spring constant is 25 newtons per meter. Remember, the unit for spring constant is newtons per meter and it's extended by 0.12. So we've got to multiply those two together. And if we do that, we get a force of 3 newtons. Okay, the next question. So there's an elastic band and this is going to send the glider away. So they've stretched the elastic band. When the glider is released, the elastic potential energy, which is stored in the rubber band, remember this is an energy store, so we've got the store of elastic potential energy in the rubber band decreases and the glider will gain kinetic energy. So it's going to go into the kinetic store. So we're going to start off with lots in the elastic store and then that energy is going to be transferred into the kinetic store, and when we've done that, the elastic store will be empty. Okay, so we are transferring energy from the elastic store to the kinetic store, and that will have no energy left in the elastic store at the end, and all the energy will go into the kinetic store. Right, the next question, what can you conclude from figure 2 would happen to the extension? So it's asking us to continue this graph. So again, it's hard to draw with the computer, but you would expect this graph to continue to curve upwards like that. Okay, and it's going to end up something like this. Okay, so if we continue that on, it would look something like this. And obviously on an exam, you're going to get some error allowance. So it doesn't have to be a perfect graph because it depends how you draw the line. But if we continue that on, we're going to get something like this. So it says the rubber does not break. So we've shown it not breaking, it's just continued to extend. So what's going to happen to it? What happens when it would increase in length? Okay, and how much would it increase in length? Well, we could say past 100 millimeters. 100 millimeters would be there. So you can clearly see that at 6 newtons of force, it's gone past 100 millimeters. The next question, what name is given to the force labeled B? Well, that's the force pulling down, so that must be the object's weight. A would be drag. Okay, so that would be A, and that is B. Which one of the following describes the downward speed of the glider when force B is greater than A? So remember, if we have one force that is bigger than the other, we get acceleration. We get acceleration because there is a resultant force. So if we have acceleration, the downward speed must be increasing. So we know that's wrong. We know that's wrong because the forces would have to be the same. So it must be that one. Okay, the next question. This is the Hooke's law experiment. So you can see here there is no mass added, no force added to it, and here we've added a weight, so we've added some force to the spring and it's caused it to extend by this amount. So which distance gives the extension of the spring? It's going to be from K to L. That's how much the string has actually extended. So that's from K to L. The next question, it says, how would leaving the ruler tilted affect the weight and extension? Data to be recorded by the student. So we need to use these keywords and we're going to write them in here. So the first one, the weight recorded by the student would be something, the actual weight. Well, tilting the ruler is not affecting the weight, so that is going to be the same. It's going to have no effect. The extension recorded by this student would be smaller. Now the reason it's smaller is because if you look at a tilted ruler compared to a straight ruler, and this extends by this amount, you can clearly see that that would not have gone as far on this one because we've created a kind of hypotenuse as if this would be a triangle. So that extension on that ruler is greater than it would be if you tilt it that way. So that means it's smaller. Okay, the next question. It says use figure 3 to determine the additional force needed to increase the extension of the spring from 5 centimeters to 15. So we've got an extension from 5 to 15. So we go across and we go down. You can see that is 2. And if we go down from that point, you can see that is 6. 6 minus 2 gives us 4. So the additional force, the increase in force is 4 newtons. That's the difference in force between those 2 points. Okay, so the next question is asking you about the limit of proportionality of the spring. So we need to look up at where this starts to curve slightly. So you're looking for whereabouts, roughly speaking, we're getting a bit of a curve. So it's somewhere around this area. Now, obviously on your exam it'll be clearer because you're going to get a much bigger picture. So we're going to say it's roughly around 7, and on the exam mark scheme it says 7.2. So all we're looking for is where does the curve start? Okay, the limit of proportionality is when it stops being directly proportional. So roughly around 7.2 newtons. Okay, so that's what we're saying there. At 7.2 newtons, the spring will no longer return to its original shape. It loses the limit of proportionality. So for an increase in force, we will not get the same increase in extension. The student repeated the investigation with 3 more springs, K, L and M, and the results are on the following page. So for this one, you can clearly see they are all still directly proportional. And the first question says, what is this relationship? So, well, I've just said the extension is directly proportional to the weight. So that's going to be that one. Okay, the next question, which statement A, B or C should be used to complete the sentence? From figure 4, it can be concluded that spring M has something the other 2 springs. So spring M, does it have a lower spring constant? Well, no, it can't have a lower spring constant because if it did, for the same amount of weight, it would have a greater extension. So that means that K has the lowest spring constant. The same spring constant, well, they'd all have the same line, they'd all be at the same point, and that doesn't happen. So it's telling you that it has the greatest spring constant. And to show you this with a bit of maths, you should by now know that force is equal to KE. So we can work out the spring constant K by doing force divided by the extension. And if we look at M, for example, we'll do it for M, then we know that the force is 10, and we're going to divide that by the extension, which is 10. So 10 over 10 gives you a spring constant of 1 newtons per meter. Okay, if we were to take the other 2 just to show you the maths, then the next one, L, would still have a force of 10 because it's still at the same point. They're all going to have a force of 10, but this one extends by more. So you're going to divide that one this time by 18, and that would give you roughly 0.55. So you can see its spring constant is much smaller, and the other one for K we'll say is roughly 10 again for the force divided by maybe 34. From this graph, if we go across, it's probably around 34, and that would give you a spring constant of 0.29, I think, newtons per meter. So you can see the lowest spring constant is obviously K, this one is L, and this one is M. Okay, showing you the different spring constants. Okay, carrying on. So the total force of the trolley on the adult. So because they're in the same direction, remember we add the vectors, so that means it's 50 newtons. Which one means the same as the total force? So the total force, or the sum of all the forces, remember, is called the resultant force. So there is a resultant force in that direction of 50 newtons. Okay, the trolley is pushed at a constant speed for 80 meters. Our work done, remember, is always equal to our force times our distance, and the force is 50 newtons from above, the distance is 80, and that's going to give you an answer of 4,000. And remember, work done is energy transferred, so it must be in joules. Okay, So with the work done is in joules, we've just said. Most of the work done to push the trolley is going to be transformed into heat. Remember, when it's rubbing on the floor, there's going to be a lot of friction, so it's going to be transferred mainly into heat. Okay, question 6 is about a power lifter, and it's given us the equation that you need to know. Remember, we've said W equals M times G, so we should know this equation, and this time, as I said in the exam, they've given you 10. So the weight is equal to the mass of 180. I'm going to multiply that by G, which is 10, and that will give us 1800. Okay? Okay, so from the previous slide, we worked out the force applied. So we said that the force on the last slide was 1800 newtons. And this time we're going to do the work done, and work done is force times distance. So work done is force times distance, so that means 1800 times by the distance moved at 2.1 is going to give us the work done, and that is equal to 3780 joules. Remember, work done is in joules because it is the energy transferred moving an object, whether it be against gravity or against friction. We're moving an object, so that is the work done. So we are moving an object. So this next question says, at the end of the lift, the power lifter holds the bar stationary above his head for 2 seconds. How much work does the power lifter do on the bar in these 2 seconds? Well, it must be 0. Why? Because work done is equal to the force, which there is a force, times the distance, but there is no distance moved. So 0 because the object, the power lifter, has remained stationary. Okay, so there is no change in distance. Now for your exam, really you should be using the term displacement, and remember, displacement is like distance but as the crow flies. So just to explain, if we had point A going to point B, or if we had A going to point B but we went via point C to point B, this could be the distance, this would always be the displacement. The displacement is the shortest path between 2 points. So displacement is often the same as distance but is always the shortest distance. Okay, the next question is about a climber, and again it's going to be about gravity because the climber is going against gravity, so he's gaining gravitational potential energy. When the climber moves up the cliff, the climber gains gravitational potential energy. So that's potential. The climber weighs 660 newtons. Calculate the work done. Well, again, work done is equal to force times distance moved. We know that the force is 660 newtons and the distance moved is 20 meters. So if we multiply those together, we will get 13,200 joules. Okay, the last question, we're calculating the power. Again, this is an equation you need to know. Power is equal to energy divided by time. So the time taken always has to be in seconds. This time it's given to us in seconds. So we know the energy is here, 13,200. We're going to divide that by 800, and that will give us our power, which is 16.5 watts. Remember, power is measured in watts.